Yes, sir.
Okay, so in Huygens principle, what he is saying, quickly we'll do a recap of what we had in the previous class. In Huygens principle, he says that each point on the wavefront, like suppose he gives the concept of, see what he has given, he gave the concept of wavefront. What is wavefront? The locus of all the particles which are in the same phase or constant phase difference is known as wavefront. So there are two more definitions. The surface, a surface of constant phase is also known as wavefront, or lines perpendicular to the light rays is also known as wavefront. These are the three definitions of wavefront. Now, what is in that? We before going to that, we discussed about wave motion. Okay, what is wave motion? Wave motion means
The transfer of energy from one particle to another.
Yeah, transfer of particles, transfer of energy from one point to another point. Only by the vibration of the particles. Particles are not going to move from one place to another place. Only the energy is being propagated from one point to another point. That is about wave motion. Next, after that, we discussed about phase. What is phase? Anyone? What is phase? It describes the state of motion and direction of a particle. It describes the state of motion and direction of a particle. Then after that we have in phase. Okay, in phase. What is in phase? In phase means the phase angle is how much? 0 degrees.
0.
Next is what? Out of phase. What is out of phase? Phase angle is how much? Phi is equal to 180 degrees. Okay. Then after that we have constant phase difference. Okay. Constant phase difference. In constant phase difference, we have what? Constant phase difference phi is equal to some angle theta between 0 to 90 degrees. Is that clear? So we give one example to remember this. I give one example for each. In phase means best example is soldiers marching, and out of phase means completely 180 degrees. And third one is constant phase difference, leading or lagging of a wave is known as constant phase difference. Now, what is a wavefront? Suppose plane wavefront. How is plane wavefront? Plane wavefront is suppose these are the rays. Okay, these are the rays. Now these are the wavefronts. Okay, these are the wavefronts. These are rays, and these are wavefront. I'm writing WF as wavefront. Okay. Now rays are vector quantity as well, whereas wavefront is a scalar quantity. Now this is said to be primary wavefront. Okay, this is primary wavefront, and this is secondary wavefront. Okay, so this dot is known as wavelength. Okay, these dots are known as wavelength. Clear? So this is primary wavefront. This is secondary wavefront. These dots are known as primary wavelength. These are known as secondary wavelength. Understood now?
So can there be more than primary and secondary?
You can, yeah, tertiary. We can go ahead like that. But for this wavefront, this is primary. For this wavefront, this is primary. Understood? That is the reason that's why we take it. Got it? For this wavefront, this is primary, and for this wavefront, this is primary. We go in that way. So this is primary wavefront, this is secondary wavefront. Primary wavelet, this one is wavelet. Primary wavelet, and then second one is secondary wavelet. If we go in that way. The wavelet is nothing but, in simple words, it is a point of intersection of wavelet, wavefront and wave ray. Okay. Now, how do we draw the how did we draw this one? See, we are taking this as this dot as a center, and we are drawing circles. All these circles will touch at a if you draw a common forward envelope, then what happens? All the circumference of the circle will touch a line, or this will become a tangent. Okay, this line will become a tangent. One second. So this line will become a tangent. This secondary wavefront is acting like a tangent, which touches all the circumference of the circle. That is known as a secondary wavefront. Okay, so we have primary wavefront, we have secondary wavefront, we have primary wavelet, we have secondary wavelet. This was described in the Huygens principle. Now, in Huygens principle also we have R is when they asked what should be the size of the circle, then immediately the question was raised, at what time you want. So we have velocity is equal to displacement by time. So we are writing here C is equal to R by tau, implies R is equal to C tau. So if you want to find out the radius of the circle, first multiply speed of light to time, what time you want. Okay, according to that, you can draw the circle or the sphere. Okay, next one. This was about, you know, this was about the wavefront, what do you call the Huygens principle.
So there's another type of wavefront, right?
We have this is the plane wavefront. Next one is circular wavefront. In circular wavefront, we write here. In circular wavefront, we write here in the circular wavefront. We draw. Suppose this is the dot. These are the rays. Okay, these are the rays. See, these are the rays. Okay, these are the rays and these are the wavefront. Okay. So these are the wavefronts. Okay. Now these dots are the wavelets. These dots are wavelets, and this one is primary wavefront. Now draw the circle like this. See, all these like keeping the dot as a center. Okay, so all these dots will touch at a particular point, and we can draw a circumference of a circle. So this is a tangent. This line is a tangent of secondary wavefront. So this is about a spherical wavefront, not circular wavefront. We say spherical wavefront. Okay, it is known as spherical wavefront, not circular. Okay. Now, after that, we have two diagrams where like they can ask one marker question. Okay, they can ask one marker question from here. So we'll do this. Three diagrams are there. Three plus two. Total 5 diagrams are there. We'll discuss that quickly. Then we can go ahead. Any doubt in this?
No, sir.
Okay.
No, sir.
Okay. Quickly moving to the next topic. That is, see, for the next week, tomorrow there won't be any class. Sunday there will be class. That also it will be evening. And next week the timing will be evening. Okay, evening 7 I will take. Okay. So it won't be possible for me to take like evening 5. Okay. Only for the next week. Now, next,
Okay,
after that, we are going ahead with the next one. What is that? About the different wavefront constructions. We'll discuss about the wavefront constructions. Now, in wavefront construction, suppose this is a prism. This is a prism. Now, this is a ray. These are the rays. Okay. So these are the rays. So what will happen? We have to draw a wavefront. So these are the light rays and these are the lines are wavefront. Okay. So just draw the wavefronts like this and draw the rays like this. So what will happen? So these rays, let it be a monochromatic, no problem. So what will happen? The rays, speak about the rays. I'm not discussing about the wavefront. So now what will happen? Draw a line like this. Draw a line like this, like lines perpendicular to the rays. Okay. So then what happens? These are the wavefronts. But in examination, most of the students in one of the board exam, when this question was given, they drew in this way. I'll just show you what is the mistake they did. They drew in this way. Many students, they drew in this way. They thought these are the rays. They cannot understand what is a difference between wavefront and a wave that is light rays. So they drew in this way and they made a mistake. Okay, so please be careful. No need to worry about it. Just draw the rays first. Draw the rays, complete the ray diagram. Then lines perpendicular to the rays will give the wavefront. There is then one more diagram that is about the convex lens. In convex lens, what we are doing, we are drawing the rays like this. So just to complete the ray diagram. So what will happen? A ray which is parallel to principal axis after refraction. After refraction, what will happen? It will
pass to the focus.
Yeah, it will converge to the focal point. Just draw the ray diagram. Now this here. Now lines perpendicular to the rays. See, this is how the wavefront construction takes place. Okay, next one. That is about a concave mirror. Okay, in concave mirror, this is so these are the rays now. So these are the rays. Now what happens? This will be after reflection, they converts to a point. Okay. So see here. So this is a point now. So this is a converging point. Clear? Now this is about you know focal this is about a convex. I am taking here. This is prism. Convex lens. This is concave mirror. Next one. Next one is what? Convex, concave lens. Concave lens. Now again same thing. This is a ray diagram now. To complete the ray diagram, what will happen after passing through the lens? What will happen? What will happen? They appear to diverge.
They diverge. They
diverge to diverge from a point, right? They appear to diverge from a point. So what will happen now? See.
So we'll pull back the rays and then take, right?
Now see here. Look at this point now. Yeah. So this is how it will diverge. Next one. This is concave lens. Next one. Convex mirror. We will speak about the convex mirror now. Now again, this is the ray. Okay, this is the ray. Now what happens? Just to complete the ray diagram. After reflection, what will happen? They diverge, right? They diverge. So when they diverge, what will happen? They diverge as if they are coming from a point, right? This is the focal point. Here also this is the focal point. Here this is the focal point. Here this is the focal point. Now what happens? Draw the ray diagram. Okay, so draw the like lines perpendicular. So what will happen? They appear to diverge. Understood? So that is how the wavefront construction takes place. Clear?
Yes, sir.
Okay. Copy this first. Then we'll go to the next one. We'll go to the refraction of light. Doppler effect is deleted from the portions. Okay. Doppler effect is deleted from the portion. See, the Doppler effect is removed from the syllabus. So before that, I would like to go with refraction of a plane wave. That we will discuss now first. There are two cases here: refraction and reflection of a plane wave using Huygens principle. Refraction, two cases: when the light travels from denser to rarer, and then rarer to denser, and reflection part. Three cases we'll finish off. Then we can directly enter into interference of light, which is one of the important concepts, because there will be definitely one 5 marker from interference. One 5 marker from the interference, no doubt about it. Okay. Now refraction of a plane wave. So the topic name is reflection and refraction. Reflection and refraction of a plane wave. Using Huygens principle. Huygens principle. In that we have. So in that first part is refraction of a plane wave. Refraction of a plane wave. Refraction of a plane wave. So 1 second. So now refraction of a plane wave. In that the light is traveling from air to glass, means less dense medium to dense medium. So this is medium 1. They have taken medium 1 and this is medium 2. Let it be, I am taking air to glass. They haven't mentioned, but I am mentioning like this. That is air to glass. Now the velocity in this one is v1 and the velocity here is v2. And these are the two rays. These are the two rays. Okay. These are the two rays. And this is the interface. This line is the interface. These two are incident rays. These two are incident rays. What is that? A dash is incident ray. Okay, A dash and BC. Now, when this is the normal and this is the normal. Now, I is the angle of incidence. Normal and I is the angle of incidence. So what will happen now? We are did I explain this before? No. Okay. So now here I is the angle of incidence. Now when the first ray touches the interface, the second ray is still in the air. So this is the wavefront. This line is wavefront, and this is wavefront means which makes angle 90 degrees. Okay, wavefront makes an angle of 90 degrees. Okay, clear?
Yes, sir.
Yes, sir.
Wavefront makes an angle of 90 degrees. Okay, and I is the angle of incidence. Okay, so now when the first ray, this is, let it be B and C. Okay, let this be B and let this be C. So when A touches the interface, B is still in air. A touches the interface, B is still in the air. Now B is still in the air. When this already refracts, what happens? It bends towards the normal or away from the normal now? It bends towards the normal, right? When the light is traveling from air to glass.
Towards the normal.
Towards the normal. So what will happen? Now, when the second ray touches the interface, the first ray has already traveled certain distance in the second medium. It has traveled certain distance in the second medium. So here, so I is the angle of incidence. So what is the speed here? V1 tau. This is the distance, and this is V2 tau. This much is the distance. So the distance is what? Velocity is equal to displacement by time, and displacement is equal to velocity into time. Displacement is equal to velocity to time. So we have V1 tau, and this one is V2 tau. And here this is angle of refraction. Here, so this is angle. How come? When this is angle of incidence, this is also angle of incidence. Clear? Why? Because this is 90 degrees. See here, this will be 90. This whole thing is 90. Now, if this is 90, if this is 90, and see this is 90. So remaining will be how much? We can write here. This is 90 minus I. This will be 90 minus I. So this also will become I. That is the reason it becomes I. Okay. Is that clear? Is this clear? How did we
Yes,
write I here? Yes.
Yes, sir.
The next one is here R. How did we get R? If this is R, the remaining will be 90 minus R. If this is 90 minus R and this is 90, this will become again R. So that is how we wrote here. And this is what?
So how? So can you tell that again?
See, if this is I, then here this will be 90. The whole thing is 90.
Yes, sir.
Okay, this is whole
No,
thing
the
is 90.
R1.
For R, this is R, right? If this is R, this is what? 90 minus R, right? This one, the remaining is 90 minus R. Is it not?
Yes, sir.
The remaining is, this one is 90 minus R. If this is 90 minus R, this is 90. 90,
Yes,
90
sir.
minus R, remaining will be R, right? To make
Yes, sir.
20 degrees.
Okay.
Sum of the
Yes, sir.
angles in a triangle. So now, we are going ahead now. BC is equal to what? BC is equal to V1 tau. And AE is equal to what? This is E. AE is equal to what? AE is equal to V2 tau. Okay. AE is equal to V2 tau. Now, we'll go with the triangle now. Triangle ABC and triangle AEC. Triangle ABC and triangle AEC. When I say triangle ABC, sine I is equal to what? Opposite side by hypotenuse. Sine I is equal to opposite side by hypotenuse. So what we get now? Now, sine I is equal to what? Opposite side is BC and AC. BC by AC. So therefore, what will happen? BC is equal to AC sine I. So what we get? BC is equal to what is AC? AC is equal to V1 tau. Yeah. Sorry. BC by AC, right? Okay, I'll write here. So sine I is equal to, we'll substitute here. Sine I is equal to what? BC is V1 tau. And AC is as it is. We are not doing anything with that. This is the first one. Similarly, sin R is how much? Sin R is equal to opposite side by hypotenuse. Then what will happen? Sin R is equal to opposite side. Okay, so what is this? This is R, right? Opposite side by hypotenuse. Opposite side is AE. AE by AC. Now sin R is equal to how much? Sin R is equal to V2 tau by AC. Okay, V2 tau by AC. We'll divide one over the other. Now let it be equation number 1. Let it be equation number 2. I am dividing one over other. Sin I by sin R. Sin I is equal to how much? V1 tau by AC. Sin R is equal to V2 tau by AC. This and this will go away. Implies what? Tau and tau also will go away. So therefore sin I is equal to sin I by sin R is equal to how much? Is equal to V1 by V2. Sin I by sin R is equal to what? V1 by V2. Clear? V1 by V2.
Yes,
now,
sir.
we have
Yes,
one more
sir.
formula here. Refractive index formula. Refractive index is N1 is equal to C by V1. N1 is equal to C by V1. N2 is equal to C by V2. N1 is equal to C by V1. N2 is equal to C by V2. And here we have N1 sin I. N1 sin I equal to N2 sin R. This is again refractive index formula. N1 sin I is equal to N2 sin R. Now, lambda 1 is wavelength in medium 1. See here, lambda 1 is wavelength in medium 1. See, this is the wavelength now. See, suppose if you draw, this is the wavelength. And here, this is the wavelength. Okay. Lambda 1 is a wavelength in medium 1. And lambda 2 is wavelength in medium 2. Lambda 2 is wavelength in medium 2. So we'll divide one over the other. Lambda 1 by lambda 2 is equal to what? Lambda 1 by lambda 2 equal to what? Which is equal to BC by AE. Okay, see, lambda 1 is this one. Lambda 2 is this one. BC by AE. But what is BC by AE again? See carefully. We got BC by here. BC by AC and AE by AC. So BC by AE means here, somewhere here. So when we solve it, it is coming V1 by V2. This one is equal to V1 by V2. This is equal to V1 by V2. Okay, that is equal to V1 by V2. So then what do we get here? V1 by lambda 1 is equal to, so remaining I'll explain. Here I'll explain in the box. Okay. So here V1 by V2, V1 by lambda 1 equal to V2 by lambda 2. Means what? When the light travels from one medium to another medium, the color of the light is not going to change. Speed will change. Speed of light in that particular medium is changing. But frequency will not change. Means color of the light will not change when it travels from one medium to another medium. So wavelength will change and velocity of light will change. Okay. Speed of light is different in different medium. So both will change in such a ratio that they will remain constant every time. But frequency will never change. Okay. So here V1 by V2 is equal to lambda 1 by lambda 2. So nu is equal to V by lambda remains constant. Okay. The ratio remains constant. Once again from the beginning, quickly listen here. See, refraction of a plane wave when the light is traveling from rarer medium to denser medium, air to glass. Speed of light in air is V1, speed of light in glass is V2. Now, these two are the incident rays. Now, A dash A touches the interface. When the first one touches the interface, the second one is still in the air. When the first one touches the interface, the second one is still in the air. So what will happen here? This is the point. Okay, B is the point. When A touches the interface, B is still in the air. Now what happens? When the second ray touches the interface, first ray has already traveled certain distance in the glass medium. Now, I is the angle of incidence. This I and this I will be same. R and R will be same. Now we know that BC is equal to what? This distance is equal to, we are using velocity is equal to displacement by time. Displacement is equal to velocity into time. Now here BC is equal to V1 tau, AE is equal to V2 tau. So now take triangle ABC and triangle AEC. So sin I is equal to opposite side by hypotenuse. Sin I is equal to BC by AC. We are writing that one. Similarly, sin R is equal to opposite by hypotenuse AE by AC. Then divide one over the other, cross multiply, then we get that one. Then N1 is equal to C by V1, N2 is equal to C by V2. N1 sin A is equal to N2 sin R. Then lambda 1 by lambda 2 is equal to BC by AE, which is equal to V1 by V2. Or we can also write here lambda 1 by V1 by lambda 1 is equal to V2 by lambda 2, where nu equal to V by lambda remains constant. The meaning is when the light is traveling from one medium to another medium, that is the ratio of velocity to wavelength remains constant in any medium, so that the color of the light or the frequency will never change. Understood? Is that clear?
Yes, sir.
Yes.
Yes, sir.
Okay, please copy this. Then we'll go to the second derivation.